Welcome back. We are in week 4 of inverse methods in heat transfer. What I'll be doing in this video is giving you a very brief review of the calculus that you require for the rest of the course, especially these couple of weeks. In the last video, we saw that there are problems within heat transfer which require nonlinear regression. And when you have such problems, so let's take the example that we saw in the last video. We saw an example of something like y hat equal to a times 1 minus e to the power bx. And we had a and b as unknown parameters. So when we have such a case, we take the cost function which we want to minimize for all the points that we have collected. So we would have something like 1 over m a times 1 minus b e to the power x bxi. Sorry, I have 1 minus e 1 minus bxi I equal to 1 to m. Very similar to linear regression, except now we use this as y hat and this as yi. So remember, this is y hat I. So this is the prediction, this is the truth, and this we square and we sum this up. And what we want to do is, of course, find out minimum of j. So we want to find a and b that minimize j. Now, when you open this bracket up here and see what it looks like, you will have terms like e to the power 2bxi, etc. Okay, so you would also have terms like a square e to the power 2bxi. All these are nonlinear terms in a and b. Okay, so these are not terms that are linear in a and b. Linear terms in a and b would look like a multiplied by some constant or b multiplied by some constant. Whereas if you see, you have an exponential here and you have a multiplied by a b term. So all these are already nonlinear in parameters. So you can't solve them using the usual techniques. So this minimization requires a different algorithm. Okay. Usually this cannot be solved analytically, unlike what we saw in the case of linear regression. So this is why we need iterative techniques. But in all of them, you will remember that you will have terms like, when you want to minimize j with respect to a and b, you will have terms like del j del a and del j del b. Okay. So just how to do this in multiple variables is a very quick review, which will be sitting within this video. In the future videos, of course, I'm assuming that all of you have undergone a course in multivariable calculus within college. In case you have not, I would request you to review this, and this few minutes that I will spend within this video are just meant for a refresher of what you would have already studied in college. Obviously, it can't be a full-fledged course within these few minutes that we have. So all these are, of course, gradients, and the simplest version of the gradient that we would have seen in school is what we call the derivative. So the 1D version, one-dimensional, one-variable version is what we call the simple derivative. Now, all of us know what the derivative means. All the derivative says is how much does one quantity change when there's a small change in another quantity. So the standard derivative we will look at within inverse heat transfer is stuff like dj dw or del j del a. All this means, as all of you know, is j depends on w. If I change w a little bit, how much does j change? That's the simple question that the derivative answers. All of you know that physically it can be visualized as the limit of the tangent. So the limit of the secant which comes to the tangent. For example, you make a small change in w, it makes some change in j. And you keep on reducing this small amount of w. Basically, you take the limit of the change going to 0. So notation that you would remember from school is, if I want f prime denoting the derivative with respect to x at the value x equal to a. So this is the way we write things. There are a few equivalent notations. Again, all this should be familiar to you from school. So we could write this also as df dx at x equal to a. So this is another possibility that you would have seen from your school days. Another possibility is to write it this way, f prime a. In case you take time, then we use things like f dot. It just denotes derivative with respect to time. Okay, so what it is mathematically, it is just this limit of f of x plus h minus f of x as h goes to 0. Now, within higher dimensions, which is what we are dealing with, we have the idea of a partial derivative. So if this is the one-dimensional derivative, if you have x and you have f of x here, the only axis on which you can change is this. Whereas in higher dimensions, when you are at a point, you can go in any direction you want. In particular, you can go in two directions, which are coordinate directions. You can go along the horizontal. And as you go along the horizontal, there will be a change in the value of the function. Z, let's say, is the value of the function. If you travel along this direction and keep on looking at what height you are at, you will see that the height changes. Similarly, you could travel along this direction and keep on saying what height your function is at. Okay, so as is shown here. Okay, so this, for example, this is a fixed y and x varies, and you can see that along that x varying, the function changes. Now, these are not the only two directions along which you can change. You can change along any particular direction. At a given point, you can go along a 45-degree line. In that case, you will have a partial derivative along the 45-degree line. We use x and y because they are convenient. Okay, you can also use a 45-degree line, a 60-degree line, 90-degree line, any line that you want. As long as you move along that line, that's still a partial derivative. Now, a simple expression that we often choose is this del f del x. In case it's a two-variable thing, would be limit at, as is shown here. If you want this at a1 comma a2, let's say this is two variable. So limit at a1 plus, you add an h, you keep x2 fixed or y fixed, and subtract, sorry, I should have put an f here, f of, and similarly f of a1, a2. So you stick at the original point, perturb the x by a little bit, and take limit x tends to 0. This will be del f del x. Similarly, you can do for del f del y, and that is generalized in the expression here. Whichever whichever independent variable you are taking a partial derivative with respect to, just perturb that, look at the original position, and take the limit as h tends to 0. Anyway, like I said, this is just refresher. You can do a lot of examples of this. We have asked some simple examples for gradients within the assignment just to serve as a refresher for you. Okay, so now we come to the generalization of a derivative. So this is the generalization of a derivative. It might seem like it should be the partial derivative, but in higher dimensions, you have other things going on. Because as we saw, just del f del x doesn't contain the complete information about the change of the variable at that point. So we visualize it in multiple ways, and those ways are shown here. Again, this is only supposed to be a refresher. Okay, so again, now imagine that your variables are here. Again, let's say the variables we are considering right now are x1 and x2, or x and y. Usually we will be dealing with w's, but x1 and x2 is something that's familiar to you from school. Okay, so once you come there, what the gradient is it is actually a vector. Okay, so notice this. Now, why is it a vector? Okay, so this requires a sort of a long explanation, so I am not going to go into that. It involves something very, very subtle. But the point is this, when I have a velocity, let's imagine some vector like a velocity, a two-dimensional vector. So let's say this is a two-dimensional plane and a point starts and it's moving this way. And at a particular point, you know that there is a direction that you are moving in. Okay. Now, usually the way we represent a vector is by its two components. Okay. So I will represent in its x component and its y component. So if you have a v vector, this will have something like v1 e1 cap plus v2 e2 cap. The magnitude of v is square root of v1 square plus v2 square. Okay. And of course, the direction is along whatever direction this is. Let's call it et. Okay, so this is the direction along which this is. You can find out tan theta equal to v2 by v1, etc. So you can find all that. Now, notice this. If I ask you not only what is the velocity along x or y, but if I ask you what is the velocity along some other line, you can still take a dot product and find out what the component of this velocity is along any particular line. So please remember this. The gradient is a similar vector. Okay, if this is not clear, please just use this as I am showing it to you. All of us know how to use it. So gradient, we would simply say, if you have two variables, gradient of f with respect to x would be del f del x1 e1 plus del f del x2 e2. This is one way of writing it. Or another way of writing it is to say simply gradient of f with respect to x is del f del x1 and del f del x2. But though this is the actual way we implement it, just like with the velocity, we represent it via the components. The more important property is the one that I have shown here. Okay. Which is that when you want the partial derivative, so when I want the partial derivative along any direction v, okay, so notice this. If I want the partial derivative along any direction, just like we had the partial derivative along x and the partial derivative along y, we can actually find out the partial derivative along any direction by simply saying del f del v, that direction, is gradient of f dotted with the unit vector along that direction. Okay, so if I have a point, again I'm showing this in 2D. If I want del f along 1, okay, so let's call this x1, x2. If I want del f del x1, all I have to do is take gradient of f and dot it with e1. Now that's obvious. When I dot this with e1, all I am going to get is del f del x1. Similarly, if I want del f del x2, all I need to do is dot this with e2. But suppose I want the partial derivative of this function along this line, and let's say this is the 45-degree line, then all I need to do is to say gradient of f or del f del v, where v is this direction, the 45-degree direction, is gradient of f dotted with the unit vector at 45 degrees, which is e1 plus e2 divided by square root 2. So this is what makes the gradient a very powerful quantity. Not only do you have just two pieces of information about what the derivative is along x1 and what the derivative is along x2, you actually can infinitely find out along any direction what the partial derivative is. And we will use this to our benefit in the next video when we talk about what is known as gradient descent. Okay. Let's come to the next idea, which is now going to the next level. So the next level is like this. We looked at the gradient. The gradient was change of some scalar value, f. F here is a scalar with respect to x, and x was a vector. Okay. X is a vector because x is position and it has components x1, x2. Now, what about if one vector changes with respect to another vector? What's an example of this? Let's say you have a velocity field. Okay, so you have velocity field, you have a flow field. So you imagine, once again, for now, let's just imagine a 2D space. Okay, and there is some fluid here. So this fluid is going to have some velocity at each point. Okay. Now, if I look at the velocity field, you can draw the contours or whichever way you wish to visualize it. At each point, the vector itself has changes. Okay, if the vector moves along y direction, it will have a change. If the vector moves along x direction, it will have a change. Now, in any direction that you move, your change will also be a vector. So just to make this clear, so let's look at this quantity called a Jacobian. Again, this is something that should be familiar to you from your multivariable calculus early in college. Okay. Ignore the term Hessian written here. I'll come to that shortly. Okay. There is a very simple definition. Again, as far as the matrix is concerned, it looks very simple in the sense that you just have to have the element, the ijth element of j is del f I del xj. For example, this is element 1, 2. So you look at the first component of f and take a derivative with respect to the second component of x. Okay, so notice this is not symmetric in general. Okay, these two terms have different meanings. So for example, if f is the velocity, then this is the derivative of the second component of the first component of the velocity, or x component of the velocity, with respect to the direction y. So how much, as we call it in fluid mechanics, how much does u change with y? So this would look like del u del y, whereas this term would look like del v del x. Okay, so those two terms in general are not the same, they can be different. Okay, now what is the meaning of each one of these? So remember, let's look at, split this row wise. What this row says is, you can now think of this as the gradient of just the term f1. So again, if we look at velocity, this would be how much does the u velocity change with each one of the spatial variables. Okay, so how much does the v velocity change with each one of the spatial variables? Okay, if you have a 3 by 3, that is f itself is a 3-dimensional vector, then how much does the w velocity change with all the variables? So on the top, you have the variable that is changing, or the dependent variable, and on the bottom you have the independent variable. And since each one of them has different components, you are going to in general get del fm del xn. So these two dimensions need not be the same. You are just going to create a m cross n matrix. So J is a matrix. Now please do not confuse this with the cost function that I showed earlier. Here J is the standard name for the Jacobian. Okay, so the Jacobian, again, you would have seen this in your multivariable calculus classes at college. So this is a matrix, and it varies, it measures the variation of the dependent variable with respect to the independent variable. Even further, we have this quantity called the Hessian, which is just like the second derivative equivalent of the Jacobian. So nothing much changes here, but you have cross derivatives. You have del square f, del x1, del square f, del x1, del x2, etc. In this case, f is a scalar. So notice this, you can make up a really horrendous function where that is also a vector, but that's no longer a two-dimensional matrix. So this is if f goes from Rn to R, means if f is a scalar. Okay, so don't worry about that. So right now we are not going to look at Hessians in the entire course. I just want to use it for one expression in the very next slide. But for the most part, you can forget what the Hessian is. As long as you understand what the Jacobian is, you'll be fine. Okay. So the important quantity or the important property we want to talk about right now is this local approximation property, which is called the Taylor series. Again, something that I'm hoping all of you are familiar with from your heat transfer classes, earlier calculus classes. The idea is very simple. Whenever you want to approximate a function, and why this approximation of functions becomes important should be clear to you by now, because most of the times we only have some piecemeal information about the function. We only have some point information about the function, that at this point my temperature, my thermocouple measured this, at this point it measured something else. What you want to do is to know what it varies like in the middle, because you want to take derivatives, you want to apply physical laws. So for that we use Taylor series. Okay. So Taylor series says that if you know the value of a function at a point, let's say x0, and you also know its derivative, then you can kind of reconstruct the function a little bit. So let's imagine this, you have a point, you know its value, and now you know its slope. So somewhere locally you can say, okay, it will look like this if you really zoom in. Okay. So if you zoom in, you can say that the function will look like this. Let's say the function actually looks something like this. Okay, so and if you know its slope here, you can say, okay, if I go close enough, it's going to look like a straight line. Okay. Now we can go further and say, I know the point, I know its slope, I also know its curvature a little bit, again locally. Okay. So locally, based on the second derivative, you can now reconstruct a little bit more. Okay, so this is just a function reconstruction exercise. You know the value, you know its slope, you also know its curvature, then you can say something like this. In fact, you can show that the famous formula S equal to ut plus half at square is literally just the Taylor series, assuming that the acceleration is constant and the higher derivatives are 0. You will recover S equal to ut plus half at square from here, the mechanics formula. So you see function, first derivative, second derivative. Now, when you have a multi-dimensional function like this, so a multi-variable case, this was a single variable case. Multi-variable case, what you need is the first dimensional equivalent is the gradient, and this is what is known as the Hessian that I just showed. So for now, ignore this. For the rest of the course, you can happily ignore this. I'll briefly refer to it once we come to the machine learning portions, but you can ignore this. Let's see if this first part makes sense. Okay. This is the part we are most interested in. So I'm going to write this again. So if I have f, the function at a point, this will be f at the original function plus gradient of f dotted. This is a dot product. Remember, this is a vector. This is also a vector. So a dot product with h is what the approximation is. Okay, so this is approximated, plus you will have some other terms. What does this mean? Let's look at this. So let's say this function is of two variables, x1 and x2, and you have the function value at some point in space, some x1, x2 you have. Now you want to know what its value will be very close to it, somewhere slightly different, and you know its gradient at that point. Okay, so this is where all our utility of gradient comes. So suppose I want to move a little bit. Okay, I'm moving a small distance in x, this is the h1 distance, and a small distance in y, this is the h2 distance. Then I can say that whatever my old value was, plus let me take the derivative in x1 and multiply it by this distance h1. Then I take, so I'll say approximately, the derivative in the y direction and approximate by and multiplied by h2. And this should be a decent approximation if that's the only information that I have. Now, if you think about this, these two terms, you can write as f of x1, x2 plus del f del x1 e1 cap. I'm going to write this as a vector, del f del x2 e2 cap dotted with h1 e1 cap plus h2 e2 cap. Now this is nothing but the gradient of f with respect to x, and this is nothing but h vector, which is what we wrote here. Okay, so you can see that it makes sense. What we have written makes sense. Okay, so this is the primary expression that we'll be using multiple times throughout this course, including multiple times this week itself. Okay, so please do remember this. The function value at a slightly different point is function value at a given point plus the gradient dotted with the distance that we are moving. So in this video, we just very quickly covered what should essentially be around a few months of calculus, but this is just a review. In the next video onwards, we will start using this idea to derive a new algorithm for optimization that should work for nonlinear problems of the sort that I started with at the beginning of this video. Thank you. I will see you in the next video.